Hello everybody. Today we are talking about exponential functions. So we've been talking about this in class now for a little while, but I still think some of you are having some trouble with it. So I want to kind of go through the parts of it again. So our formula, remember, for our linear function was y equals mx plus b, where m is our slope and b is our y-intercept. So this time we don't have m or b, but instead we have a1 and r. A1, remember, represents our initial term, the first term in our sequence. R represents our common ratio, the rate at which our exponential function is growing. So let's take a look at an example right here. So if we have an exponential sequence that has a common ratio of 2 and an initial term of 50. So first off, I'd like us to practice writing this, okay? So y equals, and I followed the same color as the beginning one, we have A1, which becomes 50 because, sorry, the wind is kind of heavy. 50, because that's our initial term, and our common ratio is 2, so the rate at which our function is growing. So what I've done now is, by having our function here, I've gone ahead and made a table that helps us describe this. So when x equals 0, up here, our y value becomes 50, which becomes our starting point of our geometric sequence. So right here, we have this right here, 0, 50. At 1, y is 100. So then the second one's going to be up here. At 2, we have 200, which moves all the way up to here. So it's growing very quickly, as you can see. That's where the exponential comes in. 3 at 400, which would be off the whiteboard already. It has to be up here somewhere. So as you can see, just even by growing by a common ratio of 2, it's getting very big very quickly. Alright, so here. So if we have a sequence of numbers that looks like this, find the equation that represents this sequence and sketch a graph of this function. Alright, so the numbers were 3, 9, 27, and 81. So obviously we can look at this and just tell what our initial number is. 3. So right? So we have to do a little bit of math to figure out what our common ratio is going to be. So we can figure from 3 to 9, it's either adding 6 or multiplying by 3. From 9 to 27, we're not adding 6 again, so we know it's not going to be an arithmetic sequence, so we know it has to become geometric then. So that's where we have multiply by 3, multiply by 3. So basically we know we're cubing it every single time. So we know that then, right here is going to be our common ratio. It's growing at an exponential rate of 3. So now we have our equation, y equals 3 times 3 raised to the x power. So again, to try and help us turn this into a graph, we need coordinate points. So again, I made a little table right here. When x equals 0, y equals 3. When x equals 1, y equals 9, 2, 27, and 3, 81. So then what I've tried to do is come over here and graph this. So I know that my starting point is going to be on the y-axis at 3, and going up for 1, 9, and then 2 is going to be up at 27, and then 3 again, 81. So that's even higher than if we were doing 2 at the rate at which it was growing. So as you can see, the initial point tells us basically where on the y-axis we're starting. If we start at 0, or the origin, it's right here. Or it can be anywhere on our y-axis. We can start negatively or positively if we have to. But the rate at which we are growing is represented by our r. So what I want to do now, actually, I brought a pen with me. I'm going to write down one I want you to try. So let's say I have a geometric sequence that looks like this. Alright, so let's say I have a geometric sequence that looks like this. Alright? So, first off, find my initial term. Alright, 25, nice job. So let's go ahead and say y equals 25, and then I put a little multiply sign there because we got to figure out what our common ratio is. So we can say that's plus 25, or it's multiplied by 2. Right here, that's plus 50, multiply by 2. So we know again that it's not going to be arithmetic, so it has to be geometric. So we say times 2, and from here to here again, times 2. So this means that our common ratio has to be 2. So 2 raised to the x power. So our equation looks something like this. So now, if we want to be able to turn this into a graph, we can create a table of x, y points something that kind of looks like this, because we know that our starting point on the y-axis is going to be 25, at 150, at 200, at 200, and so it's growing at an exponential rate of 2. So now we have coordinates if we want to go ahead and graph it. Now our graph's going to look exactly like the one we just did, because the exponential rate of 2 is the one we did on the first one. So we know what it looks like already, so I'm not going to go ahead and graph it again. But this is a good thing to go over and practice. If you're still having trouble, have your mom or dad come up and just make a sequence of numbers like this for you to practice. This way, just practice. Learn where you're seeing, basically just looking at the initial term and looking at finding the common ratio. That's the practice we need to get to. Alright, thank you very much.